Hi, I'm Shahnawaz. In last lecture we were discussing the homotopy equivalence. So let's recall that two topological spaces, say X and Y, they are said to be homotopic equivalent if their X continuous map is, say, F from X to Y, and a continuous map, say G from Y to X, such that F composed with G, that is homotopic to identity map on Y, and G composed with F is homotopic to identity map on X. In that case, X and Y are said to be homotopic equivalent. Now let us prove the following lemma, which states that homotopy equivalence is an equivalence relation on the set of all topological spaces. Homotopy equivalence is an equivalence relation on the set of all topological spaces. Proof. Reflexivity. Reflexivity is evident. This is evident since every topological space is equivalent to itself. X is equivalent to X. This is because now to prove this, we have to exhibit these two maps F and G, for which these two things, these two expressions over here are true. So if we have X over here and X over here, then we have to exhibit these two maps, say F and G. In both cases, F and G are equal to ID on X. So reflexivity is evident. Now for symmetry, let X be homotopic equivalent to the topological space Y. So if this is true, then their X is F from X to Y, which is continuous, and a continuous map G from Y to X, such that G composed with F is homotopic to ID X, and F composed with G is homotopic to ID on Y. From this, it easily follows that Y is homotopic to X. All we need to do is just to switch the roles of X and Y. From this, it follows that Y is homotopically equivalent to X as well. Now finally, as far as transitivity is concerned, let X is homotopically equivalent to Y and Y is homotopically equivalent to Z, where X, Y and Z are topological spaces. this means that this implies that there exists a pair of functions, there exists f from cx from x to y, and a continuous map g from y to z, such that g composed with f is identity on x, and f composed with g is homotopic to identity on y. Similarly, there exists another pair of functions, say a continuous function from y to z, and a continuous function from, suppose, k from z to y, such that k composed with h is homotopic to identity on y, and h composed with k is homotopic to identity on z. Now we have to prove h is homotopically equivalent to z. So note that we have x here, y and z. This is f, this is h. Now this is g, this is k. Now we have h composed with f, a continuous map from x to z, and f composed with h, a continuous map from z to x. Now let us compose these two maps and see what is going to happen. Now, sorry, this is g composed with k. Now let us compose these two maps. G composed with k composed with h composed with k. This is same as g composed with k composed with h and composed with k. So this is not k, this is f here. This is homotopic to g composed with, now k composed with h is homotopic to id on y. Now this is composition with f. This is same as g composed with f, which is again homotopic to identity on x. And similarly, h composed with k composed with g composition with k, that is same as h composition k composite with g composition, so this is f, this is f, so this is k. So this is homotopic to this is homotopic, this is homotopic. So this is homotopic to H composite with identity on Y. This is composite with K. This is equal to H composite with K. This is again homotopic with identity on Y. Sorry, identity on Z. So this proves that X is homotopically equivalent to Z. Next, we are going to define contractible spaces. A topological space X, a topological space X is contractible to a point say X in X if X is homotopically equivalent to this singleton. Now by definition these two spaces are equivalent when suppose this is over X here and this is a point here. So these two spaces are equivalent if we have a map say R from X to this point, which is little x here, and another map from this point to X. Let us note that by I. So but this is same as to say that X is homotopically equivalent to X if there exists a continuous map say R from this space X to this singleton set X. Note that this map and this function maps the entire space to this single point, so this has to be a constant map, and a continuous map I from this singleton set X to X. So this may be an inclusion map as well. So this is the inclusion map which takes X to the X, such that I composed with R, it has to be homotopic to the identity map on X, and R composed with I, which is same as identity map on this singleton set X, and hence if this is equal to here, this is homotopy as well. This is homotopy as well. Now R being a constant map, I being an inclusion map, we observe that a space X is a contractible top point if the identity map on that space is just a constant map. So let us make this observation over here. A space if a space X is contractible to a point, then so I will represent this constant map just a constant, then the identity map on X is just homotopic to a constant map. So in order to prove a space X is contractible, it is enough to prove that the identity map on X on that space is just a constant map. Another definition is called the retract. So a retract of a topological space of a space X onto a subspace say onto a subspace say A of X is a continuous map. Is a continuous map, say R from X to A, such that when we restrict this R onto A, it turns out to be the identity map on A. Note that this implies here R of X is subset of A, i.e. this maps. So if this is the space X, this is a subset A, and this here this subset A, so this is mapped identically to A. This is why this expression over here, and these remaining points these are mapped to A as well. So this entire space is mapped to this subspace. This is called retract. Now there is another definition called deformation retract. Definition: a deformation retract of a space X onto a subspace A of X is a continuous map R from X to X, such that R of X is subset of A, that is image of R is contained in A, and R acts as an identity on A. And finally, I composed with R is homotopic to identity on X, where I is just inclusion map. So if we have X here, this is space X, so we have this map R here, which takes this entire space X onto this subset over here, this is A, and this A is identically mapped onto A by this R, and I is just an inclusion map from A to R. So we have X here, then X, and then A. Actually, let us make it A over here, and this is A. Sorry, this is X. So this is my R, which takes X into A, and then we have this inclusion map which takes A into X. So this I composed with R, I composition with R, that takes X into X, where so this is actually R, because I being the inclusion map. So if this composition over here is the identity map, then we say this R is a deformation retract. Note that one can observe that, let us make this observation. If there exists a deformation retract, of X into a subspace A of X, then X is just homotopically equivalent to A. So this follows easily, since there X a deformation retract from X into A, so we have a map here which takes X, we have a map R from X to X such that R of X is contained in A, R composed with or restricted on A is just identity on A, and I composed with R is homotopic to identity on X. So this is undone, this is given. I composed with R is homotopic to the identity on X, and so this is by definition. In order to prove this, we had to prove there exists a pair of functions, suppose f from X to A and g from A to X such that F composed with G is identity on A and G composed with F is identity on X. Now in this case F turns out to be R and this G turns out to be I. Note that when we compose G with F, i.e. when we compose I with R, that is by definition of retract, deformation retract, homotopic to identity on X. Now let us see what will happen when we compose R with I. R composition with I, that is just now this I takes A to A and this R takes A to A, that is just equal to identity on A. So if this is equality here, so this is homotopy as well, this is homotopic as well. So from here we will note that if there exists a deformation retract of a space X onto its subspace, then that space is homotopic to its subspace. Now let us do a couple of examples. The first example is Rn is contractible. We have seen earlier that in order to show that a space X is contractible, we have to prove that the identity map on X is just homotopic to a constant map. So here to prove Rn is contractible, we just need to prove identity on Rn is just homotopic some constant map. That is what we have to prove. So we can define here. So to prove this thing, to prove these two maps are homotopic, we have to exhibit a homotopy. So let us define. So here let us do this as define a homotopy. Define a homotopy h of xt from Rn times the closed unit interval 0 1 to Rn by h of xt is simply tx. So we have Rn here. What we have to prove is that we have to prove Rn is contractible to some point, say 0 of x, so or some point x of Rn. So we have to prove let's take this point 0. So we have to prove the identity map on Rn is just homotopic to a constant map. So now obviously this is a continuous family of maps for different values of t. This t is in 0 1. Note that h is continuous. Also h of x 0, that is 0. So 0 is just a constant map, and h of x1, when we restrict h to 1, that is just x, and that is this is for all x in Rn, that is just identity map on Rn. So this proves that this constant map is, this implies this constant map is homotopic to this identity map. So by previous observation, it follows that Rn, hence Rn is contractible. Let us do one more example. Let us prove the topological space Rn, and let us remove 0 from this Rn. Let us prove this space is homotopic to the n-1 dimensional circle, where this Sn-1 it contains all those points of Rn whose norm is equal to 1. So we have to prove these two spaces are homotopic. Now let us define a map. So what we need to prove here, this is Rn minus 0, and here we have Sn minus 1. So we have to exhibit two continuous maps, one from Rn minus 0 to Sn minus 1, and other from the reverse direction. Say this is F, this is G. We have to prove, we have to exhibit these two maps F and G, for which F composite with G is identity on Sn minus 1, and G composite with F is the identity map on Rn set minus 0. Define the map R from Rn set minus 0 to Sn minus 1 as R of x is the vector x over its norm. Obviously, note that when we restrict R to Sn minus 1, we get just the identity map on Sn minus 1. So if we take G to be the inclusion map and this F to be the R, then we are done. We are done. Note that therefore R composite with I, that is equal to identity on Sn minus 1, or so if this is equality here, this is homotopic as well, because every map is homotopic to itself by the reflexivity condition. Now it remains to prove that it remains to prove that I composite with R is homotopic to the identity map on Rn minus this 0. So we have to exhibit a homotopy which will prove that this map and this map are homotopic. Define a homotopy. Define a map H from R and set minus 0 cross the closed unit interval to the space R and set minus 0 by H of xt. This is 1 minus t times the identity map on R and set minus 0 plus t times R. So let us take x here and x here, R of x. That is same as 1 minus t times, now id of x is just x plus t of rx is just x divided by norm of x. Now let us check whether this is a homotopy between R, this I composed with R and this identity map or not. Obviously H is continuous. So really H is continuous. Now let us check what will happen when we restrict H to 0. Also H restricted on 0, that is just x. Now if it is x, then it is just, now this is true for all x belongs to Rn minus 0. So this is identity on Rn minus 0 and H restricted on 1. So this will be just when we put t to be 1, this is 0 and this is just x by norm x. And that is just a constant. So that is just the map R. So this means that now R is also equal to I of R. There is no distinction between R and I of R, they are the same maps. So this means that H is a homotopy between, hence therefore H is a homotopy between I of R and the identity map on Rn set minus 0. So if this is so, that means these two spaces are homotopic. Therefore Rn set minus 0 is homotopically equivalent to as n minus 1. So this is it.